12 minutes delay. First, I would like to introduce our chairman, Mr. Tanaka from Tokyo University, and myself, I'm Jochen Block from the Harvard Institute. Mr. Tanaka.
The first speaker is Professor Kamal. He will present the chemistry of absorbed complexes and mechanisms of heterogeneous catalysis.
The title of this tutorial is the chemistry of absorbed complexes, a reaction intermediate in catalytic reaction. And quite recently, a book titled Catalysis to the Future has been published last year in the States. And many of the top catalytic chemists in the States, such as Professor Bell, or Samarjai, and Buddha, and so on, participated in various research. And in this book, we show the research opportunities in catalytic science and technology, and they put in order of priority, and that in detailed studies of catalytic reactions will be the most important study, and so it is quite good timing for us to do such improvement. We study reaction intermediate and the chemical reaction, and how we can carry out the individual studies of catalytic reaction. We will immediately observe the catalytic system during the reaction. We will immediately observe some chemical species. Of course, it does not follow that it is a reaction intermediate. So I personally started to study such absorption under reaction conditions more than 30 years ago. And as you know, in most of the catalytic reactions, many people study the behavior of catalytic reaction, observing the enzymes and exits of the black box. In which we study recently, we study, of course, overall reaction of metals and alcohol. I always feel that we have to study the inside of the black box and what kind of species are being absorbed and the reaction conditions. And also we have to check the reactivity of each of the absorbed species under reaction conditions. It is very important to study under reaction conditions. And to study the reactivity of those species under reaction conditions, we initiated what we call isotope scan method. And we will replace the reactant to absorb label species and keep watching the behavior of each of the absorbed species. And then label species will appear one of them, and then finally we will go to the reaction product. And so in such a manner we can really study or elucidate the reaction mechanism. And of course many people, including in this symposium, study absorption and structure of surface species. But the important thing is to study, if we want to elucidate the reaction mechanism, we have to study absorption, study the anti-reaction conditions. And also we have to study reactivity of each of the absorbed species under reaction conditions. And also those behavior should be correlated with the kinetics of the overall reaction. So kinetics and surface science should be combined, and then we can elucidate the real reaction intermediate, which is very important to study. So using such method, we can study many metal catalytic reactions, such as H2B2 reactions and ammonia decompensation and so on. In the past more than 30 years. You could estimate my age. And for instance, recently we we studied the simplex mechanism or the simplex process such as absorption and desorption. As you know, in many textbooks it is written that Lamia gave such equation. And one thing is, for instance, rate of desorption is a function of coverage. Of course, the rate constant depends upon coverage, but still, in many textbooks, they say that rate of desorption is a function of coverage. And that is the reason why many people study behavior of desorption using temperature program desorption and so on under vacuum. But we started to study such behavior when absorption is taking place. And how we can study absorption? This is what we call, we have just shown isotope government. And while absorption is taking place, this is pure absorption on parental. When absorption is taking place, this is the total absorption curve. But during this process, we switch the ambient CO, labeled CO gas, to non-labeled CO gas. And then we keep watching the behavior of such absorbed species and developing species. So, in such a manner, we will estimate the absolute rate of desorption and the absolute rate of absorption while absorption is taking place. And first, so if we study such behavior, the rate of desorption was, of course, the function of coverage, and the rate constant for desorption was plotted against the CO pressure. And it is very interesting to find out that the absolute rate of desorption of CO is dependent upon the CO pressure in the ambient. It is quite different from what they say in the textbook. And on the other hand, as to the rate of absorption, of course, we will estimate this way. And at full coverage, of course, rate of absorption comes down to zero using such technique. And so Weitkamp and his co-authors calculated the behavior of such things using computers, multi-color approximation. And so this is the pressure of CO or gas, and it will double, and then higher, still higher coverage. And please notice that, for instance, at the coverage of 0.3, this is the rate of desorption, and this is also the rate of desorption at higher coverage, at the same coverage, 0.3, and 0.3 and 0.3. So you can study, you can notice that the rate of desorption is the rate of dependent upon the pressure in the ambient. And of course, the computer gives much better results than experiment. But, according to our experiment, the rate of desorption and absorption is expressed by this equation. And in this equation, if K is unity, then it is the same as Langmuir absorption method. And as to the rate of desorption, it is expressed like this. And alpha is a function of coverage. And why such acceleration by the presence of CO in the ambient takes place? That one of the possibilities would be CO molecule stays on the surface for a while. And this is molecular experiment carried out by Harper and others. And for instance, this is elastic scattering. And in the case of CO, it stays for a while and moves around, and then it scatters in this manner. So during such just behavior, the precursor state may work reversive towards the absorbed species, and then it accelerates the resorption. And these are the constant of the absorption rate and you notice that alpha is somewhere between 1 and 0.7. And so this is the rate of aberration, and high coverage, this rate is expressed by theta, because at high coverage, then we can neglect the unity compared to this term. But as to the reduction rate and the high pressure, of course, unity in this here can be neglected, and so this is fixed. And the absorption microgram at high coverage and pressure, we can derive such equation. And if E is this one, and if alpha is almost unity, then the full coverage or coverage of this gas is almost independent upon pressure. It depends upon temperature. And if alpha is smaller than unity, then in infinity pressure, then theta comes to unity. And how is the result? Well, this is the result of 25 over the outer and other people. And as you see, the coverage depends upon pressure, but not about the here. And the saturation coverage looks to be dependent upon temperature, which is quite in agreement with the absorption microphone we have proposed. And the extremely high pure pressure, it will approach the unity. But as you know, many people estimate the surface area of managing this first little surface by using pure approaches. But in some cases, we have to be careful to use such technique on the basis of such behavior. So how about other gases? In the case of hydrogen, we do not observe absorption, assisted absorption, but in the voltage of zero, hydrogen absorption was markedly observed. And some people may say that this may be because of the CO absorption to accelerate the absorption. But actually, with CO absorption, the rate of absorption of hydrogen is not realistic. So, in this case, also, hydrogen absorption is accelerated by the presence of ambient CO. And it is not because of the presence of in the absorbed state. So, by extending such behavior, we study the influence. Then, to make a long story short, we study, for instance, methanol decomposition. And we found that the first species which was observed to be methoxide, then it comes through to fomate ion. And fomate ion decomposes. But in the case of methoxide bromine, the surface fumate ion is very stable under vacuum and at the reaction temperature. So some people may say that such fumate, surface fumate ion is not reactive intermediate, it is so stable. But in the presence of methanol, then this fumate ion behaves just as the reaction intermediate. And the reactivity of fumate ion is markedly influenced by the presence of methanol. And so we also studied infrared spectrum, which is shows some shift in the presence of methanol, but I'll keep the detailed story. And Also, this is also the case very similar to this was described by the Nobel Prize Professor Yama. And on Wednesday to talk about more in detail. But for instance, in this catalyst, iodium catalyst, where ethanol is decomposed, first they use the formation of the first time. If we decompose this under vacuum, it decomposes in dehydration takes place. But in the presence of ethanol, then we decompose it dehydrogenation. And which is very characteristic for instance, this dehydrogenation takes place, which is the amount of product per aggregate reaction time, and we zero the reaction like this. But if we evacuate in the ambient gas, then reaction stops like this. But in this case, we have a lot of ethyl sites in the surface. We can easily recognize it by means of infrared technique. But as soon as we introduce ethanol again, it decomposes like this. So the presence of ethanol in the ambient gas is markedly accelerated. It accelerates the overreaction very rapidly. And another example is folic acid decomposition, which is very famous in textbooks, and the reaction activity is plotted against fetal formation of fomate and various metal surfaces. But from the blocks many years ago, when she was young, she found that these label species showed different rates. And if fomate ion decomposition, so this fomate ion decomposition is already demonstrated, it should show two kinds of rates. But in this case, four different rates. And we studied micro still four different rate reaction. And so we studied the behavior of across fomate ion during the reaction, and we could conclude that these are the transition rate of surface fomate ion under vacuum. But in the presence of folic acid, it decomposes at much faster rate. So the reaction actually in this case between fomate ion and the folic acid molecule in the ambient. So the presence of ambient folic acid is very necessary for the high rate of reaction. We have many other examples of such kind, and briefly I just mentioned the hydrogenation reaction of ethane on oxide surface. On the zinc oxide and also zirconia, and good catalyst for hydrogenation of olefin. And of course, with those substitutes, we can easily detect dissociative absorption of hydrogen. But actually, if we study the system very carefully, we can recognize that those heterologically absorbed species are not reaction intermediates. Actual hydrogenation is Zirconia in Professor Audition's laboratory and Nicola here studied this system, and they proposed such mechanism, which is it looks like hydrogen is molecularly added to the olefin molecule, and it is same for zinc oxide and olefin hydrogenation. So in serious cases, we could study such system, and take some species on the catalyst surface, we have to be very careful to find out what the real reaction mechanism is. And especially we have to study all the behavior under real reaction conditions. And that is the thing which I'd like to express. And I used to express such emphasis such importance in the type of turbulence.
Professor Samaru, you mentioned very interesting examples concerning the formation of surface compounds. One of them was the absorption and dissorption of CO on and from rhodium. And I was thinking that there is a complicating factor that is absorption. During the absorption of CO, the structure of the rhodium is going to be changed. At the beginning we have rhodium crystallized, but CO induces a structural changes, and finally we have rhodium-1. And this process depends on the rate of this process depends on the reduction temperature of the supported rhodium and the temperature of the absorption of CO. Because the binding energy of the absorption energy and dissorption energy of CO is different from rhodium crystallized, from rhodium-1. So it might happen that there is a continuous change during the experiment. I mean, that it's difficult to get equilibrium. Did you consider this factor?
Well, yes. And you know, many people discuss it on absorption assisted stress structure and surface. And the behavior which we have observed is overall behavior, and which also should include such things as
I can't get up. You know, the problem that you alluded to at the start of your talk of observing spectroscopically or otherwise reaction intermediates is a very difficult one. You can take an infrared spectra and you see various peaks, but to relate these to the catalytic reaction is a very difficult one. The more stable ones tend to be spectator speed. Your analysis here, you've shown how you can do a transient substitution of isotopes, and that will give you some information about the intermediate. But it doesn't define what the intermediate is. You have to sort of deduce it from the type of reaction you get and what you think the surface chemistry is going to be. I guess I'm making a speech rather than asking a question, but it seems to me we're still stuck in this fundamental difficulty. I guess, what do you think?
yes, I agree with you. In many cases, that is the case. And
Most cases.
we have to thank you very much for coming. Next topic is lithium iodide